上课，然后这是他的 class today， 你是不是都讲中文啊？这是好像这样都有不能讲中文。好，开始。Yeah, I start continuing in English. Okay, just a quick reminder again. So today is October 30th, right? So we're going to finish liquids and solids. And next Wednesday, again, reminding next Wednesday, we do not have class. We do not have class next Wednesday. It's the university's fourth day, so we will not have class next Wednesday. And another reminder is, just like I mentioned last Monday, we'll have a pop quiz, right? Unannounced quiz in class will happen on Monday. One of the following Mondays, I don't know which one, but you can guess that it will be coming out soon. Right? So by the way, quiz 4 will open today after we finish the liquids and solids. Okay, this is where we were left with last time. So we're talking about latest defects. So we have two defects. One is called, they are both point defects. There are many kinds of lattice defects, but we only focus on one type, that is called point defects. And for point defects, there are two subcategories. One is called missing particles, and then the second one is called particle in a non-standard location. If we're missing particle, then what we have is so-called choky defects. Skokie defects. And the other one, if we have particles in non-standard locations, that means the total amount of particles inside lattice is the same, but just the particles are in the wrong location. It's called facial defects. Commonly seen in silver chloride, right? So that's the last time where we actually finished the class. And today we are going to go through the third phase. Right? We started talking about liquids, we finished talking about solids, and right now we're talking about gas. In this class, we didn't go through ideal gas, and hope that's a kind of a review for most of you. So we are going to actually just talk about a few characteristics of gas. The very first characteristic is vapor pressure. Right? So you can imagine that basically this is the phenomenon behind evaporation. That means if you have any liquid volatile, you are going to have the corresponding vapor form that's in equilibrium between the liquid form and the gas form. So the behavior of liquid in a closed container, initially, this is kind of just depicting if you can really start at the very beginning by pouring some liquids into a flask, in this case, which is a closed flask. So the gas is not evaporating out. What will happen virtually is some of the liquid molecule will actually evaporate into the head space. And you're going to have a chemical equilibrium between liquid phase and gas phase. And this is what we call vapor pressure. And of course, this vapor pressure will vary depending on the identity of your liquid. And just like I mentioned just now, it's an equilibrium between gas phase and liquid phase. So it's going to work as though it's a chemical equilibrium. So the rate of condensation and evaporation over time for liquids sealed in a closed container, the rate of evaporation remains constant. Rather, the rate of condensation increases as the number of molecules in the vapor phase increases, until the two rates becomes equal. At this point, the vapor pressure is 10. What does this mean? So in this class, we won't go through chemical kinetics. We won't go through chemical equilibrium, which will happen in next class. Right? But we will talk about thermodynamics. So you'll learn a little bit more on this when we talk about thermodynamics. But really, what's a chemical equilibrium is when the forward rate and the reverse rate are the same. What does that mean? Well, look at this blue line, right? It's the rate of evaporation. So initially, you have a flask, nothing inside. You just pour some liquid water into it, and you close the flask. So what will happen is the liquid water will evaporate into gas phase, right, with a constant rate because we don't change the concentration into liquid. And what really happens is as we have more gas in the gas phase, the gas water molecule will actually condense back into the solution. So we start to see actually the rate of condensation will start to increase as we have more gas molecules in the gas phase. And of course, the concentration of gas is directly proportional to its pressure. So as we have more evaporation, the concentration of gas increases, which increases the rate. Until when? Until we have exactly the same rates for the rate of evaporation and rate of condensation. And this is when we have chemical equilibrium. Because we are not going to go to chemical kinetics and chemical equilibrium, one thing to watch out for is the rate of the forward and rate of reverse do not will be the same for equilibrium. But the rate constants might not be the same. So this is what we call vapor pressure. At this point, how much pressure of gas do we have? And how do we measure this? Well, in the past, what you can do is you can pour a little bit liquid into a capillary tube. Then you fill the liquid, you fill this capillary with some mercury, and you just invert the capillary. And what's this? This is basically a barometer that measures pressure. And what will happen is, because in this headspace, right, mercury will actually flow out until this amount of vacuum actually balances out the pressure outside, right, 760 torr. And if you have liquids which will vaporize and which will increase the pressure of this empty gas space, then this is the way we can actually measure by the difference between the initial height to the height having some liquids inside. So you can see that initially the one ATM is 760 torr, right? And now we have some water, so we reduce the height from 760 to 736. So difference is 24 torr. And then to 695 and 250. So this is the way we can actually measure the vapor pressure. And of course, you can see that for water, vapor pressure is small. For ethanol, vapor pressure is slightly higher, and for diethyl ether is the highest. Right. Then, okay. Another thing you want to know is, well, we kind of didn't go through this in this class as well, since we only have 16 weeks. We kind of miss a lot of things. The number of molecules in liquid also is a given with a given energy versus kinetic energy at two temperatures. Note that the portion of molecules enough energy to exert liquid to vapor phase, but increases drastically with temperature. This is another thing that we didn't go through, unfortunately, because we didn't talk about gas. That is, this is the Boltzmann distribution of energy. And what you see is, as we increase its temperature, the height of the distribution will decrease. Right? So from the red curve here to the blue, from the red curve here to the height, and from to the blue curve here, the height decreases. Another thing is, because the sum of the area need to be the number of particles, so that means the overall tail of the blue should decrease because the height decreases. Right? So that means this whole region is the particle in temperature 2. This whole region is the sum of the particle in temperature 1. And this is the critical temperature to vaporize your liquid molecule. And as you can see, of course, for the blue, we have more than for the red. So this is in UR temperate at different temperature. And you might just question, why do we suddenly talking about vapor pressure and then right now we're talking about temperature effects on vapor pressure? Because what you can then do is you can plot the line. So as you can imagine, as we increase temperature from 0 to 10 to 20, etc. to 90, the vapor pressure inside that barometer, that headspace will increase. Of course, gas will expand, right? That's not too surprising. And as you can see, go from 4.5 torr to all the way to 525 torr. And this number is special. And then, because we have a difference, we have a change of vapor pressure respect to temperature, then what we can do is then we can plot the line. And this line is very important because this line tells us a few information. What's the boiling point? What's the heat of vaporization, etc. I'll give you the equation very quickly. So then we can really plot the line, right? So what we basically do is we just invert the capillary, look at the headspace, and as you increase the temperature, the headspace will get larger and larger and larger. Then we can use the difference in the height as a proxy for pressure. Then we just basically put a bunch of points. 0 degrees, the ideal ether has about around 200 torr, and so on and so forth. So you increase. It will be the same for ethanol and the same for water. But of course, just by judging this curve, it's very hard to say it's exponential increasing. Is it second order, third order, fourth order? So what we do then, what we can do is we can invert temperature and we take natural log of the pressure and we get a straight line. Right, so ether will be this one, ethanol will be the black line, and water will be the green line. And why do we do this conversion? Natural log on the y-axis and 1/t on the x-axis. It is because we have an equation here that directly correlates your vapor pressure to temperature. That is, natural log of P vapor equals to minus delta H vaporization, heat of vaporization divided by R, ideal gas constant, multiplied by 1/t in Kelvin, not in degrees C, and plus C. C is the offset. And what's this offset? Is the entropy of vaporization divided by R. So overall, the equation looks like this. Natural log of pressure equals to minus delta H divided by R multiplied by 1/t plus C. C is delta S divided by R. For people who already learned about thermodynamics, you realize this is exactly the equation you want for chemical equilibrium, delta G. For people who are not familiar with this, don't worry. When we go into entropy and free energy, we will talk about this equation. This equation is indeed the description of chemical equilibrium, or the chemical equilibrium constant. Okay? So, judging this by this equation again, you can see that natural log of P should be proportional to 1/t. And the slope is this term, minus delta H vaporization divided by R, plus offset when 1/t is 0, that means temperature is extrapolated to infinity, whereas line is extrapolated. And then the offset will be C. C is the entropy of vaporization. You do need to remember this equation. It's definitely going to show up on your quiz and may show up on your exam. That means from this equation, a few things you need to know. That is, for these three lines, how do we determine the heat of vaporization? Heat of vaporization is the slope, right? It's proportional to the slope, but it's negative, remember. That means the lines will be inversely proportional, right? The second is the absolute value of the slope is going to be proportional to delta H with a division of R. So for example, if the slope of diethyl ether is 1, the heat of vaporization will be 1 multiplied by R. That means it's going to be 8.314 joule per Kelvin per mole. It's going to be the same for ethanol, it's going to be the same for water. The second thing you can get out of this line is if we make 1/t 0, then delta S divided by R will be the offset. That means on this curve, we just extrapolate the curve until it hits 0. So suppose it should go beyond 0, right? This point. And this point will tell you the entropy of vaporization, but not exactly. You need to multiply by R. Right? So for example, say this point is 10, then that means the entropy of vaporization will be 10 multiplied by R. That will be 33.14 joule per mole. Right? So this is the way how you read the line here. Two things you need to know. Well, three things you need to know. The first thing is this graph needs to be plotted such that its y-axis is natural log P. The x-axis is 1/t, but watch out, it's in Kelvin. Well, this is a typo, right? Because it should be Kelvin inverse. Right? So your textbook is wrong. Okay. The second thing is you'll see a bunch of straight lines. And straight lines have two properties, right? One will be the slope. The second line will be the intercept. And the slope is directly proportional to heat of vaporization. It's going to be minus delta H divided by R, delta H naught divided by R. The intercept, the y-intercept will be delta S naught divided by R, which comes from the equation for what? For chemical equilibrium. So please, you need to remember this equation shown in green here. Okay? Any questions here? Right. Oh, there's one here. I need to finish the class 5 minutes earlier today, and then I will definitely give the time back next Monday. Okay. Do I have enough time to go through this? let's skip this one. And if we have time, we may come back here. Okay. Alright. And from that equation, right, you can see that we have natural log P. Well, we have two unknowns, right? We don't know delta H, we don't know delta S. So what we can do is now measure the pressure at two different temperatures. And as I already told you that as increased temperature, we have more particles with higher energy than what's required to actually make the liquid into gas. So that means if we increase temperature, we're going to get higher amount of gas That means pressure will increase. That's the result of this line. Then what we can also do is then we can actually measure the pressure in two different temperatures. And what we're going to get is the offset is going to be C. So natural log of P vaporization T1 at temperature 1. So you just increase the temperature and measure the pressure. And the heat of vaporization is a constant value, right? It's not going to change. And divided by R divided by T1, which equals to C. C is also a constant value, right? Delta S naught divided by R. Equals to natural log of P vaporization at temperature 2 plus delta H vaporization divided by R divided by T2. So the only thing that will change is the pressure measured at different temperature. And temperature of course change, right? T1 and T1 different. The rest will be the same. Delta H vaporization will be the same, it's a constant value. R will be the same. Delta H vaporization the same, R the same. C is just delta S divided by R will be the same. Those are properties of this this liquid. Okay? And after you finish the equation, you can quickly realize that we can move this over and move this over. So we'll get natural log of P vaporization at T1 minus natural log of P vaporization at T2. Just move this term over. And of course, this one will move it over. Then we're going to get delta H vaporization divided by R 1 over T2 minus 1 over T1. Right? We just factor out delta H vaporization divided by R. And we know the subtraction of natural log is the division of the value in the parameter inside the natural log. So lastly, we'll come down with the expression to directly get delta H vaporization just with 2 points. We don't need a bunch of points to make a line anymore. We just need 2 points. That is natural log of P vaporization T1 divided by P vaporization T2 equals to delta H vaporization divided by R bracket 1 over T2 minus 1 over T2. So watch out, it's inverse, right? T1 over T2 for pressure, T2 minus T1 for the inverse of temperature. Okay? And this is called Gauss's Klemperer equation. You're using 2 points to actually measure delta H vaporization. Alright? And lastly, we can put all this together. How do we go from the solid phase to liquid phase, then gas phase? Well, this is not something new for most of you, right? Actually, all of you. This is something middle school, right? Change of state. That, for example, for water, you can start with ice, solid state of water, H2O, and then you're going to go through a change of phase. That is when you increase the temperature, no change in temperature of the ice. But what will happen is the change of phase. Right? The ice will go to water. And then once all the ice molecule melt into water molecule, the temperature will increase. And right now what the substance is liquid water. Okay? And then hit the point where phase change occurs again, change of state occurs again, then the temperature of the system will not increase, but the phase will change from liquid water to gas water or steam. And then at the point where all the liquid molecule becomes steam, then we have an increase in temperature again. Right? So this is a typical phase diagram, where basically you plot the temperature of the substances over time when you actually heat up the substance. Okay? And then we start phase change curve. We can actually measure its melting point, the boiling point. Right? So these are the melting points and boiling points of different type of liquids or gas. Right? And of course, this will be proportional to the flow, which you can actually measure. Sorry, this is for gas to liquid. So this is the enthalpy of fusion. Right? So you're actually freezing the liquid. Okay? And the vapor pressure of solid and liquid water is a function of temperature. The data for liquid water below 0 are obtained from supercooled water. The data for solid water above 0 are estimated by calculating vapor pressure from below 0. Okay? See here? So this then brings us from that change of phase diagram to two important points on that change of state diagram. That is, we have something called the normal melting point. That is the point where the temperature increasing thermal energy does not change the temperature of the system, but it's at solid phase. Right? And then continuing, it's going to melt into liquid phase. And then at that temperature of the substance, we call it the normal melting point. That's defined as the temperature at which solids and liquid states have the same vapor pressure under conditions where the total pressure is 1 atm. Remember standard condition, that's why we call it normal, so it's 1 atm. The next point will be actually continue to increase the thermal energy of the substance, but there's no change in the temperature of the liquid. And at that point, we call it the normal boiling point of the liquid. It's the temperature at which the vapor pressure of the liquid is exactly 1 atm. Okay? Alright, with that, we can actually combine all the knowledge we learned into a whole diagram. This diagram has two different independent variables. One is we know we can change the temperature, which will change the phase. Another thing is you also know that we can change the pressure, then we can change the phase. Remember, I purposely talked about the total pressure is 1 atm. So that means if you can change the pressure, you can also change the melting, which wouldn't be surprising. So then we can really construct a phase diagram like this. Right? A phase diagram is a convenient way of representing the phase of the substance as a function of temperature and pressure. Right? So temperature increase at a constant pressure, the pressure increase at a constant temperature, and finally we come up with this diagram. This diagram has mostly three components. One is solid, one is liquid, one is gas. And also on this diagram we have multiple points you actually need to remember. One is melting point. That is at a given pressure as we go higher and higher and higher, the point where liquids meets solid. Right? For example, at 1 atm, this will be the point. And for water, this will be 0 degree. Right? At 1 atm, when solid ice melts to liquid water, we actually have a temperature of 0 degrees. So that will be Tm, normal melting point. As you continue to increase the temperature, we're going to hit another point where liquid becomes gas. Liquid water becomes gaseous thing, and the corresponding temperature will be 100 degrees Celsius. However, what's important for water is if you lower the pressure more and more and more until you reach a pressure of 0.0060 atm, and increase the temperature to about 0.0098, or almost 0 degrees. At this point, we have a triple point. What's a triple point? T3. This is where the substances coexist in solid, liquid, and gas. How can this be? Well, you can imagine a piece of liquid that is moving so freely like a gas molecule, but it also have some liquid odor like a solid. Right? Why? Because we're at a really, really low pressure. So any slight movement of this gas molecule, will actually just fly apart. But we don't have enough kinetic energy to free them, right? So when they pack together, they will still be like an older crystal. Okay? And these are the 3 points you need to remember: melting point, boiling point, and triple point. We have a fourth point you also need to remember. That is the critical point. At the critical point, we only have two phases which are indistinguishable. That is liquid and gas. Liquid and gas. This is when you are at really, really, really high pressure. That is, your temperature is so high that everything moves like gas, but it's so pressurized that you need to behave a little bit like liquid. That means the volume behind amount of liquid molecule gets compressed so much. Right? And this is called a critical point. This is triple point. Pressure is very low that solid looks like gas. Critical point, temperature is so high, but pressure is so high that gas looks like liquid. Again, triple point is pressure is very, very low, but temperature is also very low, such that liquid looks like gas because pressure is very low. Critical point is the opposite, where the pressure is so high and temperature is so high that gas looks like liquid because it's so compressed. Now it looks like liquid. So there are totally how many points? There are totally 4 points you need to remember on this graph. That is the melting point, the boiling point, the triple point, and the critical point. And you need to know the corresponding consequences of these points. Okay. And another thing that I will quickly mention, and I kind of mentioned it last time already, is this phase diagram, just by judging from the shape of phase diagram, you know this is for water H2O. Why? Because this is a really weird phase diagram. 这张图其实是非常奇怪的。曲线是没有错。Absolutely. The weird part is because the slope is negative between slopes and liquid. This is not common. This is not common. This is unique for water. That means what? That means at a given pressure 1.0 atm, solid actually, if you increase the pressure, solid becomes liquid. Solid becomes liquid, right? At this point, if we move up at a constant pressure, at a constant temperature, by changing the pressure, you can see that solid will fall into liquid. This doesn't make sense if you think about it, because if you pressurize things, they should go from gas to liquid and to solid. But for water, what's really special is you pressurize water, pressurize ice, you actually melt it. And this is, like I mentioned last time already, this is the reason why we have organisms in this planet Earth. I'll talk about it. Right? Of course, a few experiments you can do, which are quickly skin, kind of easy here. So you can actually vary at a constant pressure, different temperature, and you can actually meet different phases, right? So at 1.0, you can meet solid, liquid, gas. Experiment 3, with particle pressure, that will have the triple point. You're going to have solid, triple point, coexistence of solid and gas. So at experiment 3, we don't have a liquid phase. Solid directly supplying the gas. And experiment 2 will be the same. And experiment 4, we don't really have anything that it can distinguish liquid and gas. So we only have one phase, that is the coexistence of liquid and gas. Right? And of course, another experiment we can do is at a constant pressure, increased temperature. This will be not too surprising to you. That in this case, increased temperature at increased pressure at a constant temperature will actually slowly change solid into liquid. And this is also something really weird, right? Increased pressure, you go from a so well-defined phase to a liquid phase. It's something unique to water. Okay. And I already went through this, right? This is called regulation. Then you can use pressure to actually cut through ice. Because increased pressure, you melt ice. Something is unique to water. Okay? The consequence of this, that is actually solid water, solid H2O has a higher volume than the liquid H2O, is if a water pipe gets frozen over, because the volume of ice is larger than water, your pipe will just break. Okay? And like I mentioned already last time, this is indeed, this special property of water makes life possible. 所以这就是为什么我们到任何的外星，无论是到火星，无论是到土星，我们没到土星，不到火星，不到月亮，我们第一件事情就是找有没有水。这是一个非常 special property。为什么？因为我们知道离开了地球之后，没有大气层比较薄弱。大气层比较薄弱的话，你的温度差是非常大。所以你会突然到摄氏100度以上，你会突然到0度以下。那如何在0度的情况下，生物不会被 freeze over， 就是这个 ice 它会 float on top。那这非常重要，它保护了下面的生物。Okay, so it's the same like I mentioned already last time. This is something really special to water. The phase diagram, that is, solid water, solid H2O has a lower density than liquid H2O. That means ice will just float on top of a lake. And this is very important. Why? This produces an insulating layer that basically protects everything it needs. Right. So the low density of ice also means that ice formed on the river and lake floats, providing a layer of insulation that helps prevent bodies of water from freezing solid in the winter. Hence, aquatic life can therefore continue to live throughout a period of freezing temperature. Right. So this is something very important. And of course, the life, the application of this to our daily life is you change your boiling point at different sea levels, right? So at the Everest, the Mount Everest, the highest point on Earth, 8848. As we increase the latitude, this is altitude. This is altitude, yes. As you increase altitude, of course the pressure will decrease. Because the pressure decreases, the volume will decrease. Hence, the water will boil at around 70 degrees Celsius. At sea level is 100 degrees. And if you go beneath the sea, beneath the earth, beneath the ground, at the Dead Sea, the boiling point gets higher. Single, right? Okay. And here's some examples, right? At the top of Mount Everest, Tibet, and etc., we want to have different feet above sea levels, and you're going to have different pressures. Vapor pressure, you're going to get different volumes. Any questions here? This is kind of easy, so I'm skimming through. But if you cannot follow me, please raise your hand. Okay? This is the normal phase diagram. 这个是一个正常的 phase diagram. Why? Because you can see that the line between solid and liquid is positive. This is the normal one. And this is one for carbon dioxide, where now we have a positive slope between solid and liquid. And again, we have 2 points, right? We have melting point, triple point. We don't have a boiling point here, right? And we have critical point. So this is something really interesting with carbon dioxide. That is, it doesn't really boil. It directly goes from gas to what? To solid to gas. It supplies right away. There's no boiling point here. There's no point between liquid and solid at the 180 atm. Right? So we don't have a normal boiling point. But if we really want a boiling point, we can. We increase the pressure above this triple pressure, P3, then we can actually have a liquid and gas separation here. And what will happen is if we increase the pressure more to 72.8 atm, we will reach the critical point at a temperature of 31 degrees Celsius. Okay? So this is kind of another example for you to actually read out the normal melting point. Normal boiling point doesn't exist. A triple point and critical point. Right? So on the exam, if you are given any phase diagram, you need to be able to read out the corresponding points. Another thing you also need to is if I give you any experiment, say we are at a pressure of 72.8 atm, what will be the corresponding triple point? Well, it doesn't exist. Right? So the answer will be none of the above. What will be the corresponding temperature for critical point? In this case, will be 31 degrees Celsius. If I'm at pressure 72.8 degrees Celsius, atm, can I actually melt solid carbon dioxide into liquid carbon dioxide? In this case, will be correct. Can I actually vaporize liquid carbon dioxide to gas carbon dioxide? The answer will be no, because there's really no separation between liquid and gas in this moment. Okay, so two points. You need to read out the critical points, and you need to be able to understand how they change with different experiments. Okay. Alright, so this is kind of just summarizing. So just pay attention. Alright, any questions so far? And just like I mentioned last time, we'll finish the class 5 minutes earlier, and I give you the 5 minutes back next time. And for people who arrive later in the class, just a quick reminder, 2 things. One is we don't have class next Wednesday. It's the University Sport Day. 下礼拜3是全校运动会，所有运动课。Okay. And we also have a pop quiz, unannounced pop quiz, like I already told you at the beginning of the class, which will take 5 points of the total points, which will happen on one of the following Mondays. Which Monday I don't know yet. Okay, and which will be 100 minutes, and it's going to be just like your exam. Right? You can get an exam sheet from the TA, get an answer sheet from the TA, and just be the same, just fill in the circles. Alright, so last part, and we will finish the class. That is, so we learned about liquids. At the beginning, we learned about viscosity, we learned about capillary effects. And we learned about how different intermolecular interactions affect liquids. Right? And then we learned about solids. We started with really simple, right? Only one element, for example, uranium, for example, polonium, and we have 3 cubic lattice and 1 hexagonal lattice. Simple cubic, polycentric cubic, phase and radius. And then we have hexagonal closest band. They have a corresponding number of atoms inside the unit cell. They have the corresponding packing densities. They have the corresponding number of neighbors. Now, if we add another element to the lattice, we can start forming. Well, if you add metal, you form alloy. If you add metal and non-metal, you form ionic compounds. And then we can have the corresponding difference where the cation will fill the holes in the anion. You can fill a trigonal hole, you can fill a tetrahedral hole, you can fill an octahedral hole for closest packed structure. If the anions are in simple cubic structures, you can fill the cubic hole. How do you decide? Well, you decide by the difference, the ratio of the radius of the cation and anion. Right? So it's going to be bigger than 0.225, it's going to fill in the tetrahedral hole. Bigger than 0.414, fill in the octahedral hole. Greater than 0.732, it's going to fill in the cubic hole. That means the anion need to rearrange itself into a cube. Simple cubic. Okay? And of course, some people ask, what if it's smaller than 0.225, or trigonal hole, right? Another one, which are very uncommon, so we don't talk about that. Okay? So that's something you actually need to memorize. And the last part we just learned today about gas. But then people quickly realize there's one more thing. It's not a change in phase, we still have solid. But if you take a piece of solid and just cut it down, and just cut, until you get really tiny particle that your eyes cannot really see it, we have something called nanotechnology, lighting. Now, of course, for people who are in material science, well, maybe in chemical engineering, this is definitely in the field of interest. It's been a long time. It's been like 22 decades now. That is, the field of nanotechnology is typically defined as particles approximately 1 to 100 nanometers in size. 1 to 100 nanometers in size. That means if you can cut this particle smaller and smaller and smaller such that it reaches nanometer scale, then we reach something really interesting, and we call this nanotechnology. Okay? Because of the tiny size of nanoparticles, they behave quite differently from the normal size particle, even though they are both solids. We learned about all these packages. Even though two types of particle may contain the same type of atoms. And there are a few aspects to nanoparticle. That is, an important reason for this different behavior is the incredible surface area presenting a sample of nano-sized particle. Right, so the first thing you can imagine is the increasing surface area. Right? Nothing changed to the property, it's just it has more surface area. So you can imagine that you have a cube, then we have 6 faces. Right now you cut the cube like you are cutting a piece of tofu into a bunch of small dices. Well, of course, surface area will increase, right? Because you can see that we have an extra surface here. Right? This surface will be the same, this surface will be the same, this surface will be the same, but the inner surface will get exposed, right? This surface and this exposed. Right, so the first thing you can imagine is increasing surface size, surface area. So this extreme high surface area of nanoparticle is very useful for catalyzing the decomposition of soil contaminants, cleaning water, and so on. And of course, this is something very important nowadays. Why? Because we are thinking about hydrogen fuel cells. 那个日本、台湾都推了说所谓的氢能源汽车哦。那氢气有个大问题，就是氢气不好储存，它是气体，它又不好加压，它加到100 par 才会变液体哦。那怎么办？你想到，如果你有一个材料，它可以吸附氢气，那你要做的就是把那个材料切得很细，它的每一个表面都可以吸附氢气。那这个有没有人在做？有。最近前阵子，我不知道大家知不知道，2个礼拜前，Berkeley 的一个非常有名的教授Omayaki来台湾领奖哦。台湾有一个就是台湾的大奖，叫做糖奖 ，The Tang Prize was given to Omayaki。那他是谁呢？他是 Metal Organic Framework 的发人之一，这是我们所谓的有机金属骨架材料。那会不会得诺贝尔奖？一定会得诺贝尔奖，什么时候不知道，给谁不知道哦。那为什么要讲到它呢？因为Omayaki它可以做什么？它可以做用纳米材料来做水吸附。你可能说水吸附有什么了不起？每天打开水龙头就有水。在沙漠地区不是这样，沙漠的水非常贵，所以水吸附对于沙漠地区是非常重要的。刚才讲到氢气附，假设我们真的要做氢能源汽车，怎么样把氢气放到你汽车里面是一个大问题。我们能不能用类似的这样材料来吸附氢气 ？Maybe. And another reason for the unusual property of nanoparticles is that their tiny size allow them to penetrate into very small places, right? Another very interesting area is drug delivery, right? You can imagine that if you're just going to put a small paste of the drug in your skin, it's going to penetrate your skin. For example, one application of this characteristic developed by the Rice University was using both nanoparticle about 120 nanometer in size to penetrate the tangle of capillaries supplying blood to a cancerous tumor. The gold particles are then heated with infrared radiation, which kills the surrounding cancer cells. Okay? And we have a few corresponding materials that came out of the technology, carbon nanotubes, and so on. So this is a picture of carbon nanotubes, where basically you take a piece of graphene and just roll it into a tube. And you can imagine many things you can do with the tube. You can actually transport materials. You can actually adhere different materials on the tube. So this is a very interesting material. 这就是我们所谓的碳纤维。Alright. And there are of course many applications for carbon nanotube. I'm not in this field. A lot of things you can do with this, and so on. Of course, you can also change the size of the nanotube. Okay. So summarizing up, but not yet. Nanoscale species are ideal for biomedical operations because of their size. And one expanding involves that can increase spectroscopic detections for disease-causing cells, like infrared detections and so on. But another thing that is very interesting is called quantum dots. Quantum dots, right? These are nano-sized dots that you basically cut a severe into smaller and smaller and smaller, composed of cadmium selenide, zinc sulfides, and organic polymers attached to the molecule. And why this is important? Because something really interesting, when you cut things get smaller and smaller, that is, they change color. So you can imagine, if you have a piece of, solid, it's red. What happens is, if you cut it smaller and smaller and smaller, 你可以想象，如果你有一块红色固体，那你整个切它应该都红色。后来我发现不是啊。If you cut it smaller and smaller, the color of the particle actually change, go from red to yellow, orange, to green, to blue. So we start to realize that it's not just the size that is changing. Right? Of course, we increase surface area, but as we cut it smaller and smaller and smaller, such that it's getting to the nanometer scale, the property of the particle also changes. And one property is the color. And this is something called the quantum dots. Why? Well, we already know this, right? So when we were talking about quantum mechanics, we learned about particle in the box, right? And this is a constrained 1D box where we have infinite potential outside the box and no potential inside. And what will happen with your standing wave is you're going to have one wave here, and another wave here, another wave here. Right? And you need to fix the boundary condition. And we learned that the energy of this thing is going to be what? It's going to be inversely proportional to a length. If you make a length smaller, the energy gets higher. Hence, the energy level separation between the states. Hence, the light gets emitted out of the particle. So you can imagine what happens if you cut the material smaller and smaller and smaller in nanoscale. You can imagine that the electron inside the material is confined in a 1D box or two-dimensional box with a sphere. But it doesn't really matter, right? Because it's going to be 1D in every direction. Okay? And reaches such a point that the light emitted has a constant, has a given wavelength. And this is indeed the idea behind quantum dot. Right? So what very interesting, using the idea of particle in the box, we can explain the corresponding color of the quantum dots. And why is this important? Because the next generation display, 你们的手机的荧幕现在都是 OLED 嘛，对，大家都知道是有机材料、有机发光材料。那有机发光材料好处是什么？就是以前的 LED 啊，它要发光，它自己本身不发光，所以你要有个背光元件在后面，它真的发光。那这些 LED 材料就是吸了这光之后放出想要的光，放出蓝光也好，放出绿光也好。但是很麻烦呢，就是我把手机关掉之后它还亮，它实际上有个背光在那边，只是我们把它调得很暗很暗很暗。后来发现 OLED 这个材料它可以自发光，也就是我通电之后它就发光，也就是说我不需要一个背光材料。那这个差别在哪里？差别在于无机材料跟有机材料差别。但是我们刚才讲，就是无机材料有特色，就是如果把它切得越小，越来越小，它就有不同的颜色，而且它的发光效率会上升。所以 next generation display, even Apple was working on this. That Apple terminated this research. It's called QLED, quantum dot LED light emitting diodes. Basically, you can imagine the screen of your phone will be dispersed with different size of particles. This particle will just get light up at different voltage and will emit different light. A lot of people are working on this. Samsung is working on this. They already have micro LED display getting out, but it's too pricey at this point. It's more for demonstration. Alright, and of course for this quantum dot one number price. So quantum dot one number price this year? No, that was last year. Okay, so this kind of almost like from the previous class. Right? Nobel Prize was in chemistry was given to chemistry in 2020 was given to these three people: Mookie Bondi, Louis Ross, and Alexei Akimov. He's Russian. For the discovery that if you cut a piece of solid to smaller and smaller size, you can change its property. Alright, that's all for today. I need to finish early, 5 minutes earlier. And the answer for today is quantum dots. Of course, this won the Nobel Prize. And this will definitely revolutionize our display technology. 是很多公司都在做这个，台湾其实有人做，但是你也知道台湾的 display 现在这个飞机不强。那主要在推的就是神送啊、LG啊，还有。Right, and that's all for today.